Okay, that was the concept of ergodicity. Now we are going to move on to spectral analysis. And we will not go very deep on the subject, but we'll sort of make an introduction. And I will try to describe what spectral analysis is, and I will try to derive the power spectral density and try to make a sense of it for you. Okay, essentially, the spectral analysis stems from this first observation. The magnitude square of a signal is a measure of the energy it carries. Okay, at which frequencies the signal is stronger, let's say. And by signal here, I'm referring to a random process in our context, but in general, spectral analysis is applied to phenomena, what we call signals, right? If you have taken a signals and systems course, you should be familiar with this. And if not, no problem. Understand process when I say signal, okay? So in particular, we are interested in the power a signal carries at certain frequencies. Okay, we would like to know at which frequencies the signal is concentrated its power on. Okay, and why do we need this? We want to be able to separate, filter, or design the signal on different frequencies to have some applications. And some obvious applications are in communications, right? We have different frequency bands both in, let's say, broadcast technologies like television or radio, etc., or uh, double-sided communications like cellular communications or other types like satellite communications or Wi-Fi, etc. Basically, any wireless medium, you are interested in the spectral analysis of your signals so that you can use the channel, the airwaves, simultaneously for different users because we're separating the frequency band for different users or different applications so that you are making use of um, multiplexing, which we call multiplexing. Okay, you're making the channel available for multiple users at a time because they're at different frequencies. So for that, you would like to be able to design the signals as well as understand which signal belongs in which band. We also have radar and related applications and remote sensing, for instance, well, using, let's say, satellite imagery, and let's say, detecting types of crops, types of some, for instance, geological properties of your land, let's say, whether you have oil inside it or not, etc. Or clearly audio processing and speech recognition, an obvious application here because well the spectrum of some let's say voice signal or sound signal is going to carry information about the source of the sound, or maybe you can process any given sound signal. Maybe you would like to make it clearer, maybe you would like to change it in a certain way, maybe you would like to amplify certain frequencies, etc. Maybe you would like to correct it. Maybe if you know some applications in in entertainment and industry, for instance, there are a lot of applications in speech processing and audio processing, obviously also image and video processing because high frequency in images and video corresponds to changes, rapid changes. For instance, in video, you would like to know when the scene is changing rapidly so that you encode that portion of the video in a more delicate way. Maybe you put more information for those frames. But if the scenery is not changing much, that means less frequency. So that means less change. So maybe you can encode it using less number of bits, which makes your encoder maybe more efficient, etc. And information security, right? For instance, you would like to detect abnormal behavior in the packets, maybe coming into your system, your servers, etc. maybe someone is trying to penetrate your defenses. Maybe there is a denial of service attack going on, but maybe it's a little bit stealth. It's not really obvious. So that you need to analyze the data in such a way that you would like to obtain information about outliers, okay? What is expected and what is outside of it, what is abnormal. Maybe you would like to detect such activity. So we have applications in information security. Also in astronomy, cosmological data, like the light readings from space, they indicate certain events in obviously in distant past. So it sheds light on the dynamics of galaxies, and maybe it sheds light on the structure of the universe, and also how it came into existence, etc. And also a very important application in financial signal processing, right? Maybe you would like to model the dynamics of the market, or maybe you would like to estimate the behavior of the prices of some shares. In that case, spectral analysis is highly useful to apply time series data. Okay, so as you see, spectral analysis is quite important and has a wide variety of applications. So we are going to see a very brief introduction to spectral analysis in the context of random processes.